Hello guys, and welcome to our channel Curious Chips. And in this STA series we will be going ahead with our third video. So in this video we will start with how STA tool works or how timing analysis is performed using the tool. So whenever we perform any of the timing analysis, what we need some of the inputs, right? So what does that consist of? Netlist as in gate level netlist from the different stages of the design phases. Secondly, constraint, that is SDC, which is having definition of clocks, false path, MCP and all that, which we will be discussing later. And third is like dot leaves and timing data. So these all inputs we will be requiring to perform STA on our design. So what does the netlist consist? Netlist consists of the design information, like what is the functionality and how is the design connected to each other. Constraint consists of what is the timing requirement, what are the false paths, what are the paths to be checked, and by how much timing that needs to be checked. And what does the leap timing and data consist of? Rise time, fall time, functionality of the cells, total delay of the cells, all the timing data related to delay. So when performing the STA, these are the inputs and these are the requirement to go further. But when we give these inputs to the tool, what does it do after receiving these inputs? Let's go ahead. So now that you have the netlist, SDC and dot libs of the design, and now you have the tool as well. So when we give, so this is the tool, when we give all the inputs to the tool, what does the tool does? It analyze the design. What does it mean? Tool understand what is the design about, where are the combinational cells, flip-flops or sequential cells, what are the primary inputs, primary outputs. I know this just for your understanding, this video will be taking much more time than the regular one, because it consists the basic fundamentals of the working of the tools. Okay. So when the tool understands the netlist like combinational cells, flip-flop, sequential, primary output, primary input, paths, etc. So when the tool understands these things, it applies SDCs, constraints on these things. Okay, but how does the tool knows when to apply, where to apply, and how to apply, right? When, where and how does the tool know for applying the constraints on the design and what to take from the libs? So for that, when we move ahead, when the tool understands the design, it turns the design into DGA. What is this? Directed cyclic graph. Directed cyclic graph. What does it mean? So the tool takes the design and converts it into nodes and edges. Suppose this one is node 1, node 2, edge 1, edge 2, edge 3, edge 4, another one node 3, another edges, edge 5, edge 6, edge 7. So the tool what it does is divide the design into DCA, directed cyclic graph. So what does this node have? As we discussed previously, it would be having primary inputs, primary outputs, flip-flops, pins, etc. And what does the edges have? Edges would be having like the combi path, clock path. So for example, if I give you, suppose this is the flip-flop, these two are the flip-flop, and data is passing from this combinational logic from flip-flop 1 to flip-flop 2. So this is considered as node 1, this is considered as node 2, and this is the edge. Okay, so this is one of the edge and node pair. Okay, so on this the tool tries to apply the constraint. So what is the clock frequency? Okay, so we get the period of from where we get the period of where the data should be launched, where the data should be captured, like this. And the combinational cells, like if we have, we will drop this one, and the combinational cells in this, like if we have AND gate, OR gate, this or NOT gate, so these timing delays are being taken from .lib file. Okay, so the total delay of this is taken from .lib, the clock to queue and the flip-flop timing requirement also taken from .lib. So now we have from point A, if we see the node flip-flop 1 as a point A, so if we have the flip-flop this one A and B and combinational, so now we have the node A going to node B, and this is the delay. So like this the tool represent each and every path inside the design into the DCG. So the tool converts all the design into different nodes and edges, and there are different types of paths on which different ways of SDCs are applied. So what are the different types of paths we will study in the next video. What are the different types of constraint that will be in the next video. So just for your understanding and the basic structure of the tool, this is the taken as input, converted into directed cyclic graph, and the SDCs are applied on it, taking the delay values from the libs. So this is all the overall structure of the tool, how it works. So in the coming video we will discuss about types of path and how the SDCs are applied on these nodes. Thank you.